All right, so we've seen a lot of great talks at the JVM Language Summit talking about JVMs and hearing about what people are doing with different languages on the JVM. This talk is going to look at multiple languages and JVMs from a slightly different perspective that I still hope you'll find interesting. I will try to end up a little bit early since we went long in the last session, and hopefully that'll give you some time for questions, and I look forward to hearing what you think about it. So this is my first time at the JVM Language Summit, so I thought I'd tell you a little bit about me. I work at the IBM Toronto lab on JIT compilers. I've been doing that for about 13 years. I'm the current architect for the Testarossa JIT compilers in the IBM JDK. And I'm leading a secret project, which is the topic that I will be talking to you about today. But first, our lawyers assure me that there is a gripping legal tale in this slide and the next slide, and I highly encourage you to go back to the slides and read through it in case it has any impact whatsoever on how you interpret what I say. First of all, I'm going to give you the story behind this talk. So I'm going to start off purposefully telling you about a problem that IBM has been facing for a while now, and just talk about the secret path solution that we have been working on to address that challenge. Now, I know you all traveled here from all parts of the globe to hear about IBM's problems, but bear with me. Some of those problems aren't just ours. I think they're actually problems that people in this room are going to experience as well. And so the talk is going to end with an open proposal and a request for feedback on the work that we've been doing, and just want to hear about what you think about what we've been doing. So our stakeholders mostly talk to us about Java. So I'm from the JVM team, so people normally just talk to me about Java. So we hear lots of things about Java, 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 Java. What should we do with Java? What's not working in Java? What should we be doing differently? But a while ago, it wasn't all about Java. Some people started talking about some of the other languages. And, you know, it would be nice if we could ignore those people, but they're our customers. They're people who are going to be using our products. And so we started to listen. And now we've found that it's actually lots of different languages. We still have a lot of people who are interested in Java, but there are other languages that are now showing up, from JavaScript to Python to Ruby to you name it, lots of different dynamic languages. And yes, even COBOL. We do keep hearing about things that are happening in COBOL, and there are advancements going on in COBOL. But I won't talk about that very much today, because I know it's not really a dear topic for this room. There are a number of reasons behind this, I think. I mean, the number of open communities and investment that people have made in making those languages much more powerful and capable and useful for solving problems that people are really wrestling with, coupled with the ease of deploying applications from many different runtimes in the cloud and platform as a service infrastructures. And finally, just the trend towards microservice architectures, where we're no longer building these massive monolithic applications in Java. We're breaking those things down into much smaller services that can be actually written in whatever language is the best tool for the job. And so this is actually a great thing. This is not a problem. But from IBM's perspective, we have our own JVM implementation. We find maintaining even one language is a pretty costly affair, right? You have to keep up with advances in hardware platforms, making sure that you're exploiting all the new instructions, all the new capabilities that keep coming. We have to keep up with competitors. Thanks. Although I think that's actually a very good thing about the Java ecosystem, right? Having lots of competitors working on the JVM implementation has actually been very good for the Java ecosystem, and it's driven us to do a lot of performance improvements that might not otherwise have happened quite as rapidly. You know, we have to do lots of hours of testing, writing new tests, fixing all the problems that customers find, as well as even the ones that we find ourselves before we inflict them on the rest of the world. And then all the sort of activities that go on around the development team, writing documentation, managing the project and releases, and engaging with stakeholders. And oh yeah, this thing called innovation, which actually pushes forward the state of the art in the runtime that we've got. So let me just look at the top one there. Now, we've heard a couple of times today that x86 is the only important platform. Maybe ARM, uh-oh. Throwing the mic around. Sorry about that. So we've heard that x86 is the only important platform here. You're going to fix this? It is? Yeah. It's too slippery, I guess. Okay, all good. Funny, I'll have to say it again. We've heard today that x86 is the most important platform. It's not actually the point I'm trying to make, but I'm making it very well. IBM, on the other hand, has customers that run across a number of different platforms. So we have our own Power architecture, we have our mainframe architectures, and these are actually very important. We have very big customers running on all of these different platforms. And we have different operating system variants on all of these three major hardware platforms, which add another multiplicative factor, and I haven't even taken into account 32 and 64-bit compressed refs and all those other variations, little endian versus big endian. All of those variations makes it extremely painful to implement and maintain even one language runtime. So as soon as there's one hardware advance on one of these platforms, we really have to surface that in the runtime. And if you start adding more language runtimes, so if we were to take the same approach that we took with Java and implement a parallel implementation of all of these language runtimes, we would have to do all that work over again. We'd have to pick up all that work and repeat it in another runtime. So for 2, that looks bad, but maybe we could pull it off. 3 starts looking really worse, and once you start getting to many languages, it's very clear that this is not going to scale at all. And so for IBM, clearly the approach that we're using for Java is not going to be the thing that we're going to be able to use to address the needs of our customers going forward, and new customers. And the thing that really makes this challenging is all the existing language runtimes are completely different implementations. They have JustinTime compilers, some of them don't. They have GC technology, they have threading models, they have mechanisms to cooperate among different threads, but they're all implemented completely differently. They're completely different implementations. So even if we were to work in these different runtimes and try to surface the support for our hardware platforms in all of these different runtimes, it's still a lot of work, because no matter what you do, in the Java space, we'd have to pick up and apply that leverage in different runtimes, and we wouldn't be able to share very much of that knowledge, implementation cost, effort, etc. So it's looking very costly for us to support multiple language runtimes in the way that we've traditionally done this. Now, that's not an unfamiliar problem to everyone in this room, right? We're here to talk about JVMs and languages running on top of the JVMs, because that's a great way to leverage all of the investment that's happened in the JVM. And that provides great interoperability with Java, which is, we get to leverage that large ecosystem of both programmers, developers, and code, as well as all of the JVM implementation details under the covers. So we get great JITs, we get great GC performance. There's a little bit of an impedance mismatch between what the JVM is implementing in terms of the JVM specification and the thing that the other language runtimes want to implement on top of. But that's a problem that obviously has been recognized and we're working towards. We've seen lots of talks talking about how the details of the JVM specification can be massaged to help other language runtimes operate better. And this has been there's a very successful community of JVM implementations. Lots. I was looking on a Wikipedia page, there's 56 different languages that run on top of the JVM, and that's great. But IBM had a little bit of a concern with leveraging the JVM in this particular way, because in a sense, it divides the language community by imposing trade-offs, right? There's trade-offs in the runtime that are imposed by using the JVM, and then there's also there's trade-offs implied by using the JVM to run these different languages. For some languages, the division in the community doesn't really matter, because the language was created on the JVM, it runs on the JVM, there's a single community on the JVM, so that's not a big issue. But many of these existing languages, like Ruby and Python, have a vibrant non-JVM based community. And if you're forced to choose between 2 different runtime implementations to run your code, that can make some quite stark trade-off choices, right? You may want high performance, but you may not be able to run with all of the extension modules that make that community vibrant and great. And I know there are some talks later in this, maybe even later today, that are going to go into detail on some of those issues with accessing extension modules via the JVM, which has traditionally been a pretty bad problem. So, and even bridging this divide would mean really migrating an entire community either one way or the other. And so IBM, we have some experience with being another JVM implementation and seeing some of these migration and compatibility issues. Java as a language was really almost designed from the start to have multiple implementations. It has a really well-defined JVM specification. It has a really well-defined language specification. And these are great. They do help with implementing multiple implementations, but they don't cure all the problems, right? There are always compatibility issues, sometimes bug-for-bug issues, which can be particularly frustrating, and behavioral issues because the specifications aren't, fully complete. There are areas of the specification that are implementation defined or that they aren't, they aren't actually specified. And so you end up getting it doesn't work that way on the other one kind of statements. And these migration issues, as we've heard earlier, are really kind of turn customers off. They really don't like to migrate either from one runtime to another or even to later versions of runtimes. So we decided to experiment with a slightly different approach. So I don't want to characterize this as a competitive approach. It's really, I think, it works together with the approach that's being taken to use languages on top of the JVM. But we wanted to experiment with a different approach that would allow existing runtime communities to leverage the strengths of the technology within the JVM. And so the secret path from the title of my talk is really to unlock the VM within the JVM. So I think from the last talk that Cliff gave, you can see that there's a lot of technology and a lot of stuff that's been built inside the JVM that doesn't necessarily need to have a Java flavor to it. We may have implemented it inside a JVM for the purpose of executing Java, but those technologies don't need to be written in that way. In fact, we could refactor them in order to distill out the Java specificity of those components and have a language-agnostic core set of components for things like JIT compilers and GC technology. And then it might be possible to lift those language-agnostic components out of the JVM and integrate them into other language runtimes to try to migrate some of the capabilities that we've spent so long building in the JVM and investing so many people and hours and money building, and we can bring those capabilities to other languages for a much lower cost. And so what we would get if we were to do that would be a toolkit of language-agnostic components that could be used to build language runtimes and augment existing language runtimes. And so you could pull out that VM and you could integrate it into, say, the Ruby MRI runtime and use it to bring JIT compilation, GC technology, other tooling capabilities. Or you could do the same thing with CPython and leverage these components these ways. Really what we're doing is we're establishing a different API into the components that we've built rather than using the JVM specification, which despite all of the efforts that we're going through, is still a JVM specification. It's a specification for a machine that runs Java, even though it's getting a lot better at running other languages as well. So, the secret experiments that we've been performing with our production JVM, we've been working on refactoring the components within the J9 JVM, which is the IBM JDK, to create this language-agnostic toolkit designed for being integrated into other language runtimes. So things like memory allocators, thread libraries, platform port library, event hook frameworks, tracing engines, garbage collectors, JIT compilers, a lot of the code that implements the things that you just saw in Cliff Click's presentation that are present in the IBM JDK are now being refactored so that we can actually pull those out and apply them in other language runtimes. We then performed a bunch of experiments to try to integrate some of those components into other language runtimes. And Ruby MRI and CPython are the two that we chose as basic proof points to see how well does this experiment work. Now, this is a lot of work, so it's been a long effort. The refactoring job is a tremendous activity to apply to a code base. And so we knew that if we started this and did it in a side branch, it would just never merge back into the real code base. And so rather than doing that, our product development team has actually dedicated some resource over the last couple of years to doing this aggressive refactoring in our code base while we're developing the new releases for IBM JDK8, which we released earlier this year, and IBM JDK9. As that development is proceeding, it's going alongside with all of this refactoring. And that's an important proof point for the fact that it's not just that you can take these components out and put them somewhere else. It's that you can take these components out, treat them as a toolkit, augment the toolkit, and reintroduce them periodically into those other language runtimes. It's a model of consumption rather than just, here's a starting point, go wherever you want to go from there. We want to be able to build something that you could actually continue to innovate in and push innovations into multiple different runtimes. So in performing these experiments, we took a bunch of different components from a runtime and integrated these core runtime infrastructure, so utilities, a threading library, the port library, VM structures, all of these things along with a tool agent. We incorporated those into Ruby MRI and into the CPython runtime. And then that enabled us to start doing some of the more exotic components like a trace engine, the garbage collection technology, and the JustinTime compiler. And there are other things that we have tried that I'm not going to talk about today, but I'd be happy to discuss after the talk. Okay, and so there are several proof points that we decided to implement. So method profiling is something that's not always easy in other language runtimes to get a very good view of where the time is being spent in the runtime, because these runtimes are written in C, and if you use standard profiling tools to try and find out where time is being spent, you find out that various bytecodes and bytecode helpers and various guts of the runtime are being used, but that doesn't help you connect back to the language that your program is written in, the functions and methods and blocks that your code is written in, to find out what are the pain points that you need to worry about. We also ported our entire our garbage collection framework into both of these runtimes to provide some interesting capabilities. On top of that, we also got some verbose GC output, which is something that's not always available. It helps you understand what your garbage collector is doing, as well as some of the visualization tools and the insight tools that we have around using the garbage collection technology. And finally, JustinTime Compiler. We incorporated some simple JustinTime compilers into these languages which don't exist right now. And so I want to report on how successful we were. So, method profiling. So just as a backgrounder, IBM has a tool called Health Center, which can automatically connect to, if you ask it to, connect to a JVM, and it will, with a very lightweight overhead, it will tell you what methods are consuming time within the JVM. So you can see here there's a histogram on the top pane showing just where is the most time being spent in this little application that this is demonstrating. And then the lower pane is actually showing call stacks, so you can actually break down if something took a lot of time, where was it being called from most of the time. And the way that this gets implemented is actually by a trace point which feeds call stacks periodically to the Health Center tool. And so we took that same trace point and incorporated it into the Ruby runtime, leveraging all of the infrastructure that we had already ported into the runtime to handle the trace points and to connect to the Health Center agent. And for free, we got Ruby method profiles. So the top pane again shows time being spent in Ruby code, and the lower pane shows the call stack from the Ruby stack representation within MRI of where those calls were from. So this is a good example of just picking something up from J9, plugging it down into the Ruby MRI, and bang, you've got an extra capability that you didn't have before directly from the runtime. The second experiment we did was with taking our scalable garbage collection framework and incorporating it into CPython and MRI. So it's our GC is type accurate. It's actually a very scalable, high performance, multi-threaded, parallel, concurrent, you name it, all the buzzwords that Cliff mentioned in his talk for how, what you need to do in order to have a high performance GC. We have that. And so we've done this refactoring job to distill the Java out and take the garbage collection framework and introduce it into the Ruby MRI runtime. And for free, just because, it is a type accurate framework, of course, because it's used in Java, But in this case, we're using it in a conservative sense because the Ruby MRI garbage collector is conservative. And the reason for that is primarily so that extension modules can continue to operate the way that they operate because they're not tightly aware of what the garbage collector is doing, so it's not careful enough and doesn't maintain type accuracy. So, and since not breaking extensions is an important goal for us, we decided to just step down and do conservative GC. So another advantage that we got of introducing this collector technology was Ruby MRI, the heap is actually a set of slots that are constant size, and most of the memory is actually being hung off of the heap in native memory. And what that means is it's really hard to control what the size of the Ruby heap is because, well, most of the data is actually somewhere else, and it's not in a managed environment. We were able to make some changes into the MRI. Now, this wasn't as low touch as some of the other changes that we've made, but we were able to actually instrument to find all those allocation points and move that data from native allocation onto the heap and with variable sized objects. And now the GC can manage all that size. So you can say if you want a 4 gig heap, you can get a 4 gig heap. If you want a 100 megabyte heap, you can have a 100 megabyte heap. And that actually does more or less reflect the memory usage of the Ruby program. So one of the interesting capabilities that we got out of that was just a verbose GC output, which I don't believe Ruby MRI has. You can just say dash verbose GC and bam, you get XML output that's shown here. Sorry, it's a little bit small, you probably can't read it, but it's just basically giving a lot of information in detail about what the garbage collector activities are, what GC phase is happening, how many objects is it finding, how much memory is it collecting, how much memory is left on the heap at the end of the cycle, how long did the cycle take, and so on. So similar to the method profiling view that Health Center can provide, it can also provide a GC visualization, so it can actually take the data that I just showed in text and XML form on the previous slide. Using trace points, it actually gets the same data to the Health Center tool, and so it can provide a visualization of what's going on during GC pauses, when they're happening, how long they take, how much data is being collected, again, the same type of data, and it can visualize that for you. So we actually didn't have to do anything here because the GC technology that we picked up out of J9 already has the trace points in it. We put it down inside of Ruby MRI, did some stuff around the edges to make it work inside the Ruby runtime, and we got that same tool for 0 changes can provide a visualization of the GC activity that's going on. And we could also do that for CPython. Sorry, I didn't have a graph of that for the method profiling stuff before, but we can also do this for CPython. Same basic premise we just picked it up, put it down, this trace points got generated, the agent communicated it to the tool, and the tool can visualize the data that's coming out. Another tool that we have is it's called Garbage Collector Memory and Memory Visualizer. It's a tool that can provide more deep insights about the activities of the GC. It can provide tuning recommendations, options, settings that might help tune the performance of the garbage collector. It's based on the verbose GC output that we just saw. So because we get the verbose GC output, this tool actually operates just as well for Ruby MRI as it does for Java. And it can indeed provide recommendations on options that you can tune with your GC so that it can improve its performance. Just-in-time compilers. Okay, so Ruby MRI and CPython, neither of them have JIT compilers. There are other Ruby implementations like JRuby and Rubinius and other CPython implementations like PyPy that have JIT compilers, but the reference implementations which are written in C do not have JIT compilers. There are lots of reasons why JIT compilers are tough to build for these languages. There are people in this room who are much more able to explain the challenges of trying to compile languages like Ruby and Python than me, so I will defer that. But basically it comes down to the very dynamic capabilities and mechanisms that these languages have. Also, there's unmanaged direct access to VM data structures because it's C, you can write extensions in C, they can reach back and look for things and twiddle things and change things, all unbeknownst to anybody. And so that makes it a real challenge for the JIT compiler to actually optimize anything because it has to be maintaining the state that anybody can reach in and look at and see. And if you do, you'll break something which kind of goes against the compatibility concerns that we had. Finally, there's some design choices in the runtimes themselves that make it difficult to write JIT compilers for. So one of the examples here is the Ruby MRI uses set jump and long jump for exceptional things like iterating and calling blocks. And this is actually quite a challenge. It's quite an interesting use of set jump and long jump that makes it rather difficult to incorporate native compiled code into the same environment. So our efforts to date here have really focused on trying to get to the point where we have compiled native instructions. We want to avoid making big changes to the runtime so that it's not too difficult to adopt. If this becomes of interest to these communities, it wouldn't be too hard to adopt these compilers into those runtimes. We want to provide consistent behavior between compiled code and interpreted code so we don't have those compatibility and migration issues that we were talking about. We don't want to place any restrictions on the use of native code and extensions, modules for either Python or Ruby. And so the last point, I guess, is just that this isn't a super mature effort at this point. We haven't done any benchmark tuning. We haven't done any benchmark specials. We're really not exploiting very much profile information about what types are flowing through the program at this point. We're really just trying to do a proof point and experimental and just demonstrate that it's possible to pick up the compiler from J9 and put it down inside one of these other runtimes or both of these other runtimes and get compiled code performance for relatively easy effort. Remember that there's a recurring theme here is that we want to maintain compatibility. We want the community to be able to stay together while they're picking up all the code that we're picking up. And so actually the proof here is that we can run Rails. And that's true for all of the stuff that I've talked about today for the method profiling support, the GC technology, and the JustinTime compiler support. We can run Rails. And that's a pretty strong statement because Rails is not an easy thing to get working. All right, just a little bit of background on the JustinTime compiler component that is inside J9. So it's called Testarossa. It was originally built as a Java JustinTime compiler. It has a fairly standard flow where you build the intermediate language from the bytecodes. That flows through a sequence of optimizations which improve the quality of the intermediate language. That then flows down through a code generator which can generate code for either Power or x86 or mainframes. And there are a lot of queries that the compiler has to make while it's compiling code. There are compile time connectors to talk to the J9 JVM. We built compile time connectors for Ruby MRI and for CPython so that you could ask questions, so that the JIT could ask questions. Also it has a large profiling framework that it uses in the Java environment. We're not currently using that within the Ruby or CPython environments. And then finally, there's a runtime aspect of this, which is sort of support for the code, a bunch of runtime helpers. It manages the code caches, and the metadata that's associated with the code so that things like stack frames can be walked and so on. The compiler was built as a Java JustinTime compiler. However, over the recent years, it's actually been expanded to target 8 different languages, including COBOL and an esoteric language that only exists in IBM. None of you will have heard of it, but our economy probably depends upon it fairly substantially. All right, so results. So this is a Bench 9K performance, a subset of the Bench 9K benchmarks. It's not a particularly awesome set of benchmarks to use to measure just-in-time compiler performance. There are lots of compilers that do a lot better than this. I'm not going to say that we have fantastic, stunning numbers here, but I think if you put them in the context of the requirements, the constraints that we're operating inside, and trying to maintain compatibility and ease of adoption within the runtime, these are actually pretty good results. So on x86, which I know is the platform everyone here claims to care about, we have 3 benchmarks that are above 2 times performance, and a number of ones that are, everything's above 1, some of them not very much above 1. Like I said, we haven't done any benchmark tuning here at all. This is just basically the results that we get from a straightforward application of our technology into this runtime. There's lots of low-hanging fruit here that we know of that would make this a lot better. optimizing things like method-to-method dispatch for JITted calls and so on that would make a huge difference here. But we just haven't done that because it's now because Testarossa is a retargetable compiler framework. It's already built to compile on x86 and Power and our mainframes, Z systems. We automatically get results for Power. Now, these are not as great results as we saw on x86, and obviously we'll be very motivated to go and look into why those differences are there, because in principle we should be getting relatively similar performance on Power as we would get on any other platform, because we haven't done any target-specific stuff right now. We've basically just gone to the process of converting the bytecode into our IL, running a small set of optimizations on that IL, and then just letting it flow through the code generator. And so, so for free, once we had done that, we got x86, we have Power, and we also have it running on our mainframes. So all of these are on Linux, for example. Again, similar kind of performance profile for our mainframe systems, and that was basically for free. We didn't have to do anything special to get that. Final proof point here is the fact that we actually used this code base to release our IBM JDK8. So this released at the beginning of the year. You could argue that if we were doing this work and it slowed down our ability to deliver other code or other releases, that would not really be a very successful thing, right? We want to be able to use this technology in many different places without interfering with anybody's release schedules. And so I'm happy to say that our JDK8 release was as good as any release that we've done. In fact, there's a number of new capabilities that we added. It coincided with the new release of the Z13 mainframes, and we did some pretty amazing stuff to exploit all of the new features that were available in those machines, as well as a number of similar kinds of things in the Power architecture. So we're doing a lot of work across platforms. We do have a big team working on this, but we managed to do all of this aggressive refactoring and take that code and reuse it inside of other runtimes at the same time. So I think that's actually a pretty impressive thing. We also managed to release some COBOL compilers at the same time, but So we think our results are pretty promising, but it's all secret, so like who cares, right? Well, I am here talking about it. We realized obviously very early on that these are not just problems that IBM's facing. IBM is very large and it has all of these concerns all together, but that doesn't mean that these concerns aren't also true for everybody else who's using different language runtimes. So I think most of the people in this room can probably read through this list of challenges that IBM faces, right? We own our own platforms, we own our own operating systems, we're building cloud and PaaS infrastructures, we own lots of different tools that have to access lots of different runtimes, we have large data centers that benefit from optimizing and improving the resource usage for efficiency, and we have lots of developers and customers who are working with multiple runtimes. Probably everybody in this room can pick at least one line on that list and replace IBM with your name or your company, and that statement would be hopefully at least partially true. And so that means that everybody in this room could benefit from the type of work that's happening here. So we think this is a really common set of problems across our industry, and we would all benefit from having these language agnostic components that we could use in a number of different ways. And even IBM has figured out that these languages really exist in the open. And so that means if we really want to have the broadest possible access to the components that we're talking about, we have to create an open community around these language agnostic components. And so that's what IBM's going to do. Our vision here is to create a community of contribution around this toolkit of components that can be used to build VMs for any language. The fundamental toolkit is language agnostic, and that means that it's a good place for all of us to work together, individuals, communities, corporations, to safely collaborate on building new and better VM infrastructure, right? You don't have to just use the infrastructure that's in one runtime. We can pull it all together, and we can work on it together. We can work on the pieces that are common, and we can innovate ourselves on the pieces that differentiate for our own interests. It will enable everyone to focus more on innovating instead of just building the same old wheels that we've been building in different language runtimes over and over again. So It will also have the benefit that it will provide a more robust core technology for all of these language runtimes, because we're testing it from a number of different scenarios. We'll fix bugs once, not 5 times in 5 different runtimes. It would be a great place to collect best practices, share learning, and do things like this conference to try and share what's going on in this area. And it also would mean a lower barrier of entry for new languages, right? So if there's this core set of core toolkit of components available, if you want to create a new language runtime, it's relatively easy to pick up something that's language agnostic and specialize it for your new language idea. And so we can test new ideas and get much more effective results and test them more reliably. So I'm almost done, but I have a few parting thoughts. So almost no one starts a new project saying, first I'm going to write the firmware from scratch. There are people who do that, but they're usually writing firmwares. No one says, I'm going to write the file system from scratch. No one says, I'm going to write the display drivers, unless you work for a video company. We'd like to make these statements just as unlikely. I don't want to have to write a cross-platform port library from scratch every time that I want to work on a new language runtime. I don't want to write a new garbage collector from scratch every time I want to write a new language runtime. And I don't want to write a new JIT compiler from scratch either. Now, there have been some projects in the open that are being very successfully used on some of these fronts. But we think a community built around trying to solve all of these problems together is really a very effective approach. And so I'm keen to hear your feedback. We think our results are encouraging. What do you think? On the idea. Yeah, the idea. The proposal, thank you, I like it. Yeah. 2 thumbs up. Yes, please. Awesome, thank you. So some of the challenges that we're currently experiencing here, so we would like to create an open source project around these language agnostic components that come from the J9 JVM technology. Our code's not quite ready to open up. There are some low-level components, some of the earlier components on the diagram that I showed of, do this, then this, then this, then this. Some of those are ready, but some of the larger components aren't yet ready. So for example, our JIT compiler right now, we still have to disentangle many of the other language support that, like COBOL, that you're not interested in, from the parts that we do think would be reusable in a language in a project like this. We're currently fighting a little bit of a battle to balance the work that we're doing to refactor these components to make them open source ready with trying to make our proof points more compelling, right? So try to push up those performance bars so that everyone goes, wow, that's amazing, that's great. And then finally, we want to engage with communities and partners, and we need to figure out the right ways to do that. And so I guess I'm here to say, what do you think? And do you have any advice for us or any feedback, or would you like to get involved? And you can talk to me now, or you can send me email, or you can send our CTO, John Dujmovic, email, and we would love to have a conversation with you. Questions? You had your hand up earlier.
What's the license, and IBM legal taking it?
IBM, well, okay, so I wouldn't say we've gone through all the hurdles there, but what we're working towards right now is we're looking at an Eclipse Foundation project, which would mean it would be under the Eclipse license, which means a very friendly license for any type of use, right? As I said in an earlier slide, we want these to be broadly accessible to as many people as possible. That doesn't mean putting restrictions on how you can use it. Yep, I can understand that. I'd love to see it go away too.
But you were able to take it out?
No, we did not. Sorry, we did not do that. We have not done that work. But we have some ideas for how we might try, leveraging some of the expertise that we have building in the J9 JVM. So, the issue of cooperative suspend came up earlier in the context of hotspot. So IBM's JVM is a fully cooperative suspend model, and it does have rather efficient primitives for figuring out how to lock and how to keep everybody in the right frame of mind. And so taking a parallel technique to that, not necessarily taking the code that we're using in J9, which is actually very complicated code to understand and track. It's whenever you're trying to do something very aggressive and multi-threaded and high performance, you end up with complicated nitty-gritty code. But the basic approach, I think we could try to migrate that. It's just not an effort that we've started yet.
I mean, it's definitely one of the hot topics
Yeah.
in Python.
Yeah.
To see that happen.
Yeah.
I think what you address in terms of the GC is definitely one key part of that in
Right.
terms of removing reference counting. I would imagine.
Yeah.
And although I'm curious how that works with the C extension API.
It does work. So we did have some issues incorporating the GC into CPython, and you might have noticed that the GC results that I presented were from Ruby. We've had more success with integrating the GC into MRI than with CPython. We do have some lingering issues, so I can't claim for sure that we've solved that problem. But we have done the work to integrate the GC into CPython, and it does work. We didn't change reference counting, although we did do a few experiments on the side to try what would happen if we took away the reference counting aspect and just relied on a mark sweep approach for CPython, with the obvious consequence that you lose timely finalization. And so, that's a migration issue because there are lots of extensions that actually rely on timely finalization, and so, we kind of backed off from that as not really an interesting experiment to do by ourselves in secret. As a proof point.
Sounds good. You should get the Python Language Summit next May. Talk more.
Yeah, I'd really like to do that. Yeah. Charles.
Cool stuff.
Thanks.
I have one question. Well, I have one question in two parts. The first part is, to what extent do you think the design choices of MRI are going to limit how far you can go with this?
Yep.
I mean, as you listed a bunch of these issues.
Yep.
Those are exactly the issues that have kept Koichi and the others from
Yep.
even trying to go down this
Yep.
path,
Yep.
or at least not do it aggressively.
Right.
So from your experience.
Well, so there are a number of them. It would not be a small effort, and so in our view, we thought it would be better to make the compatible, see what we could do by staying compatible, see where we can get to. Hopefully that's a compelling argument to at least get involved and start, sort of working with the community. I think there are a number of things that we've learned, along the same lines as Cliff's talk, things that we've learned from building J9 over the past 20 years that could be brought to a runtime like Ruby, that we can try to help, change some of those fundamental problems. But as is, I don't know. Like I say, we can still make improvements.
Basically say at some point the C extension API has to be removed, replaced with something.
It does have to be fixed. It will definitely limit the viability, the effectiveness of a JIT compiler. Like we'll never see numbers like JRuby shows for these types of benchmarks. I don't think. Maybe it's possible. Like I say, there's still lots of low-hanging fruit that we could push on. I guess I'm dubious that within the constraints of the existing system that we could actually make that happen without making large-scale changes in some very complicated parts of the runtime. For example, exception handling, which is always an extremely tricky part of any runtime design. In MRI, it's not pretty either.
Right.
So.
Well, and then the second part is,
Yeah.
You've obviously taken a look at Rubinius as well and how they're doing things. They do have C extension support,
Yep.
but it's incredibly expensive
Right.
through their indirected handles.
Yep.
But as a result, they have better GC, better JIT.
Yep.
Is that an approach that you are interested in looking at?
Yes.
Because
Yes.
depending on how many C extensions are in the system, that
Yeah.
overhead can overwhelm the performance
Sure.
of the system.
Yep, that's true.
And they're seeing that when people run
Yep.
stuff on Rubinius too.
Yep. So, the way Java gets around this is by the definition of the JNI and the indirections that you perform in order to get access to anything that's actually from within the managed runtime.
Right.
Providing that same facility in another language like Ruby, along the lines of maybe what Rubinius has done, is one way to get there. And then the fact that it makes performance slower, I'm not sure, that would be a compelling reason not to just do that. But if you had other things that could make up for that performance, like the advantage that you'll get by doing that is the more freedom from the JIT compiler to optimize things. Right. Right. So you get on. It's Cliff mentioned this earlier, right? You have to get off the path that you're on, get onto a new path, and then that gives you the longer runway to get to higher degrees of success.
Okay. Cool. We'll have to talk tonight too.
Yeah.
Are the implemented languages, are they able to interoperate? Like Python is able to interoperate with Java, for instance?
Right. Yes. So that's an issue that. So it wouldn't necessarily interoperate at the Java level, but we could at some point drive interoption at a lower level. So the API or the specification of these lower level components is at a language agnostic level. If you can surface the same API through different things and you have the same connective tissue going on between the different runtimes, the opportunity for interoperability is there. It won't be as seamless as trying to work with Java objects and pass them around. But I think the interoperability issue or capability is possible. You have another.
So does the language runtime get to control the object layout, or does the GC
Yes.
enforce some
Nope.
object layout?
No, the GC is language agnostic. It does not. Part of incorporating the GC technology into a language runtime is the language runtime specifies what the object model is. And then the GC works within that. It queries the language to say, how do I find out what this thing is? Here's a pointer that you told me is live. Tell me what other pointers it points at, right? Other blocks of memory that it points at, and then I'll walk those ones too.
Can you fork?
Yes.
Hey.
Although it's not pleasant. But basically we introduced pre-fork, post-fork kind of collection points to make it work, right? And then we can bring threads up in the fork process or not. Yeah.
Does your changing of the two languages change their cold start performance?
That's a good question. We haven't measured that.
I know that kills your stuff.
So it would have an impact. So the JIT being introduced does. The current JIT that we've incorporated is synchronous, so you block to compile code. The underlying JIT technology that we have in J9 is multi-threaded, asynchronous. We just haven't taken that code and brought it across into these runtimes. So in principle, we could get that same startup performance. Startup performance is something that J9 is well known for doing very well at, right? Via things like shared classes and dynamic ahead of time compiled code. So bringing those capabilities over into these other language runtimes should help with those types of issues as well. Any other questions? One more.
Question.
Oh, good.
Hotspot guy, what do you say?
That sounds like a weird question. Code-based can be worse.
All right.
No one rises to the challenge. Okay.
What was the question? I'll rise just because I'm obnoxious. What was the question?
So what do the hotspot guys think of this work?
Oh, this stuff? Go to town, guy.
Cool. All right. Thanks, everyone.